I want to echo the sentiments of thanking Bary for what's been an amazing workshop and morning, afternoon sessions, and then the evening gatherings, the whole deal. So thank you very much for putting that together, and thank you for the opportunity to participate on, as well. Okay, so uncoupled higher order learning and games. We've heard all of these words already in the course of this workshop. Maybe feedback systems, not so much. This is largely the work of recently defending PhD student Sarah Tunsi, and I'll mention briefly some of the things that are going on with Hassan Abdurraouf, which we'll mention also that Yorgos Pilioris is a co-author on that work as well. So we'll start with a quote. The attainment of equilibrium requires a disequilibrium process, and indeed Peyton mentioned kind of this quote in spirit of having the cart before the horse. Here's the equilibrium, and generally one says, these are the dynamics, what's the equilibrium? But here's the equilibrium, what's the dynamics? And there's a lot of work that's happened in this area, and here's a handful of monographs from folks in the room on the topic. And the focus, if I may, here is we have these solution concepts. We'd like to kind of understand some plausibility argument of what could lead to these solution concepts. And the landscape looks something like this. You can imagine a really big matrix, okay? And the rows of this matrix are properties of games. And so there's potential weakly acyclic, contractive, zero-sum, what have you. The columns of this matrix are different types of learning rules. And again, there's a host of those learning rules. And the outcome is going to be what happens when you take this type of game or the game with this property and match it with this learning rule. And that's the outcome. It is a very, very big matrix. It's fair to say that it's mostly filled out by Sergio. Can I say that? And, so here's my meta theorem for, if you ever played Mad Libs, for game property under learning rule, strategies will outcome. Okay, and so then a lot of the results follow that template. And so here's three that follow that template and prior work. For zero-sum matrix games under smooth fictitious play, player strategies converge to Nash equilibrium. Now, that's a convergence result, but there are non-convergence results, and sometimes you keep the learning and change the game, and it doesn't converge. So for the Shapley game under smooth fictitious play, player strategies oscillate. Or you keep the dynamics or change the dynamics and keep the game, and things don't converge. For zero-sum games under replicator dynamics, player strategies do not converge as well. So you see that there's a few moving parts here of the game or the learning dynamics if we're going to focus today on convergence to Nash equilibrium. But then there's the one game to ruin them all. We have here a three-player game. Player one wants to be different from player two. Player two wants to be different from player three. Player three wants to be different from player one. And they have their utility functions have some coefficients that reflect a preference of how they want to be different. This game has a unique mixed equilibrium, and here it is. It's everything we're doing is finite matrix games over the simplex. And you see that the equilibrium, curiously, the equilibrium strategy for player one depends on a coefficient of player three, a player who's not even payoff relevant to player one. So if player one is only looking at player two, because that's the player who's payoff relevant, somehow their equilibrium strategy depends on that of player three, the one who's looking at them. And this goes all the way around. And it's now been 20 plus years that Hart and Mescalel said that for the anti-coordination game under uncoupled dynamics, player strategies cannot converge to Nash equilibrium. Okay. So let's mention again what's uncoupled learning dynamics. In uncoupled learning, learning rule does not depend on the utility of other players. It can depend on what players do, but not why they do it. Okay, so if we're engaged in a congestion game, I don't like congestion, I might want to avoid congestion. Maybe you're not in a hurry to get to work. There's a meeting that you want to avoid. Maybe you want congestion on that day so you can say, sorry, I was stuck in traffic, okay? So I can react to your presence, but not to why you're there. And so that's an uncoupled learning. I can react to what you do, but not why you do it. And so what are some examples? In smooth fictitious play, it is uncoupled. Replicator dynamics, finally on the board. It can also react, it is uncoupled. Where this red letter P, since we're looking at matrix games with multilinear utilities, that is in fact the gradient of the utility function for each player. Okay, so they're using this gradient to move in a certain direction, whether it's smooth fictitious play or whether it is replicator dynamics. As you know, or as you can see, the gradient is a function of the other player's actions, but it's not a function of their utility functions. So it doesn't depend on their utility function characteristics. So again, I can react to what you do, but not why you do it. So now, a common feature that all of these dynamics have, and it was a feature that was very smartly exploited in the paper of Hart and Mascolel, is that the order of the learning dynamics match the order of the strategy. So if you look at smooth fictitious play, there's a number of states. The number of states is the dimensions of the strategy space. Replicator dynamics, the number of states is the strategy space. And consequentially, the movement of strategies depends on the current value of the gradient. And what we'd like to say is what happens if you use the history of the gradient, a little bit more sophisticated processing of the gradient. It's the same informational structure. So it's still uncoupled. It's just processing that information a bit more kind of complicated or sophisticated way. And so this would be an example, and this example is very much in the spirit of optimistic gradient or other things. If this is the standard order dynamics that reacts to that gradient vector in a certain way, let's take that gradient vector, pass it through another dynamical system, which requires auxiliary states, and then react to the modified gradient, where the modified gradient could be a combination of the gradient that we had and its history. So for example, this is how the gradient has been moving. Let's use auxiliary states to get some sort of myopic anticipation of where it's going and react to where it's going instead. That's fine. It doesn't change the informational requirement. However, it is now a higher order learning rule. It has more states. And so if we revisit this one game to ruin them all, actually, it turns out that one can maintain uncoupledness and convergence to Nash equilibrium if one allows the use of higher order states. Okay, so this came out, again, 20 years ago. For the anti-coordination game, anticipatory versions of replicator dynamics, smooth fictitious play, do indeed converge to the mixed strategy Nash equilibrium. So uncoupledness plus fixed order is a barrier. Uncoupledness without fixed order restriction is not a barrier in this game. And these are a few other older papers that explore similar themes in more general settings. So you can find this idea around. In optimization, there's the various versions of higher order in time. Optimization, heavy ball, accelerated, optimistic gradient's been mentioned a couple of times. In the 2000s, you'll find some work that to get around the lack of convergence for zero-sum games that was observed, and pretty much this amounts to optimistic implementations or variations. And then there's work in the 2000s, and then work in the more recently than the 2000s, and the terminology that we're very glad to adopt was by paper of Laraki and Mertokopoulos on saying higher order learning. When we're adding auxiliary states, they looked at a particular sort. I'm going to look at a different sort today.
There's a Zelton paper on anticipatory learning, probably from the 90s.
I'll add that, yes. Thank you, thank you. Yeah, you pointed out when I mentioned to you the other night, or the day, yeah, you pointed me to that's the Crawford puzzle, okay? And I guess it's your namesake, right? Okay.
It refers to my 74 econometric paper.
Yes.
Instability, extraction,
Mm-hmm. So the main results for today are as follows. We'll show that what happened with the anti-coordination game is not a one-off. Okay, so for any game with a isolated mixed strategy Nash equilibrium, there exists out there some uncoupled rule that will work for that game, and robustly so, will work for nearby games. And it doesn't need to know the Nash equilibrium in advance to work. And so it's any mixed strategy Nash equilibrium can be learned by an uncoupled rule. But while we have a universal structure, we do not have universal parameters. So for any such uncoupled rule, the ones that we'll talk about today, you can construct a game for which it doesn't work. Okay? So for every game, there's an uncoupled rule that works. For every uncoupled rule of our sort that works, you can construct a game for which it doesn't work. By work, I mean converge to a isolated mixed strategy Nash equilibrium. But then we're going to show, I think, what's actually the most interesting part of this is that although we can, doesn't mean we should. There are some mixed strategy Nash equilibria that are learnable, but require a sort of irrationality in the learning to be able to learn them, and I'll mention what that is. The setup that we're going to have today is going to be, again, just a standard finite number of players, finite number of actions. We'll be looking at differential equations evolving over the simplex. And for convenience, we'll just look at multilinear games. So you can imagine a game on a graph, and the player is playing pairwise against everyone who's on that edge. And again, this is a convenience assumption that we can get around. For the sake of today, our baseline dynamics are going to be what we call target gradient play. And so target gradient play, this is the standard order version. This is where I am. This is my gradient. Move in that direction. But if I overstep, project it to the simplex. That's my target. And minus where I am gives me a velocity. This will be our baseline dynamics. There can be other baseline dynamics, but this is the one that we're going to use because it's particularly convenient in the current setting. And we're going to build off of this standard one to do higher order ones. So an important enabler for us is to rewrite learning dynamics as open systems. So what do we mean by that? This is how we just wrote target gradient dynamics. The gradient was built in. A player comes with a utility function, and they use that utility function in their learning rule, okay, as we're seeing here. And so there's the red letter P. It is the utility. It's the gradient of that player's utility. It's built into the learning rule. This is what I mean by learning as a closed system. But we're going to write learning rules in this way. Instead of reacting to my gradient, I'm going to react to some external stimulus called the letter P. And that's it. The letter P has been brought up in Panos's talk. This letter P was the expected utility for each action. Okay, so it's how it's going to be used here as well. But we want to write learning as an open system. So for us, a player doesn't come with a utility function. A player is a behavioral rule. That's a player. Okay, so this is a player. This is a standard order target gradient player. If this player is in a world with one other player, that's where the letter P comes from. If this player is in a world with two other players, that's where the letter P comes from. But so it's players don't know the utilities of others. They don't even know their own utility, because for us, a player is just a reaction to this letter P. And that allows us to write things.
Pi does not depend on xi, but can depend on x minus I.
Yes,
right?
yes,
That's,
yes. Yeah, yes, yes, yes. And so in the two-player case, this is what the diagram looks like. We have a diagonal process in the forward loop. Those are our two players. And then we have a process in the feedback loop that blends them. Okay? And why is the forward loop diagonal? Because we're insisting on uncoupled dynamics. I can't peek at the letter P of another player. So again, a player is an open system. Uncoupled means that it's diagonal. And if we change the game, the players don't change. Okay, so the game is just what fills in the feedback loop. So there I said it, the word feedback. This is what it looks like in a more general setting now. A player is any dynamical system mapping the trajectory of P to the trajectory of X. A causal dynamical system, we are silent on what's the order of that system. As long as it's not telling the future, that's what we call a player. Okay, so it's implicit whether this is standard order or high order, but we will insist that it is diagonal. Okay, and why is it diagonal? Because we insist that this is uncoupled learning. The game just fills in the blanks, okay? So we get our players and then we insert a game. Now, what's happened is that convergence to Nash equilibrium has become a question of feedback stability. We're looking at a feedback loop. Convergence to Nash equilibrium is a question of feedback stability. For me, this is great news. I don't want to sound like I'm bragging, but feedback control is my domain, okay? No. Go to feedbackcontrol.com and you'll see, you'll see that it is my domain, okay? Okay, so let's do the first result, okay? Any isolated, completely mixed Nash equilibrium.
This is for you.
Yes, yeah.
This is for us.
Can be locally stabilized robustly by a suitable uncoupled higher order dynamics. So our starting point is going to be target gradient play, and we can generalize to other starting points. But our starting point is target gradient play, and this is what our higher order version looks like. Target gradient play is still responding to P, but it's responding to a P plus dynamic processing. There's two parts to the dynamic processing. One is something that's called a washout filter. The washout filter does the following. If P converges to a constant, the washout filter turns off. Okay, so it has the property that if it is excited by something that is converging, it stops what it's doing. And so that's going to assure that we haven't really shifted any equilibria because this is going to stop what it's doing. And then after it exits the washout filter, it just gets modified. So you can think of this as a generalized Rmax if you come from that world. Okay? It's just going to take its history and process it into something, and then that something is going to be added to the original letter P and pass through our favorite baseline dynamics of target gradient play. And so it's an additive modification. There are other types of higher order. The one by Laraki and Murtakopoulos does not fall under this structure when they looked at higher order replicator dynamics. And there are others that do other maneuvers. But for us, it's going to be additive. We have the pre-processing part. Yes, sir.
So UI is the current, what's UI?
UI is whatever's coming out of this dynamical system. And so these letters, E, F, G, H, have yet to be, yes.
Blue box, whatever.
Yes. So we have here the washout filter, which has the turn-off property. It's going to be processed by some dynamical system. Out comes UI, and we're going to take that UI and add it to P. Okay.
Sorry, what's NI?
NI is on the next slide. It's a bookkeeping. It's a projection to annihilate the vector of ones. It's the null space of the vector of ones. Okay. And that will get rid of kind of scale, additive constants to the letter P. And so here's the full state space detail, if you like. The washout filter is a dynamical system. This other box is a dynamical system. And NI is bookkeeping to annihilate a vector of ones. And that allows us, it's important, it's more than bookkeeping, it allows us to talk about convergence to a Nash equilibrium without knowing the Nash equilibrium. We are going to linearize around the Nash equilibrium, but the linearization is only for analysis. We don't really know it when we build these dynamics. Okay, so here's now, again, a picture. We have business as usual target gradient play. And then what we've done here is we've isolated all of the higher order modifications. If higher order modifications are 0, it's business as usual. If we're going to put some dynamical system behavior here, then it's not business as usual, it's higher order target gradient play. And this, again, we insisted on being diagonal to maintain uncoupledness. So local stability of a Nash equilibrium is equivalent to the existence of a diagonal system, dynamical system that renders this feedback loop stable. Does there exist a diagonal dynamical system that renders this feedback loop stable? That's the question. That is a question that was asked extensively, actually, explored extensively in the 70s and 80s, actually, in the controls community. And so here's the more formal statement of the result. If we have a completely mixed Nash equilibrium of a matrix game that is isolated, and here's where isolation comes from, a particular matrix being non-singular. Then there exists a higher order target gradient play for which it is locally stable, and if you change the game without changing the learning rule, it is still locally stable to some degree. So it has a built-in robustness. This is not a razor's edge. What's the Nash equilibrium? Swim to it, okay? And so all mixed strategy Nash equilibria are stable. The idea behind the analysis in the controls world was something called the decentralized fixed mode. There are instabilities that can be handled if the two channels are talking, or if multiple channels are talking to each other. So what we have here is a eigenvalue at 1. One of the agents can do something about it, but can't see it. Can't see when it's blowing up. The other agent can see it, but can't do anything about it. If it was centralized, they can talk to each other. But so this system cannot be stabilized with a diagonal controller, okay? But there are rank conditions that as long as your system satisfies these rank conditions, then it can be stabilized with a diagonal dynamic controller. And it turns out that for isolated mixed strategy Nash equilibrium using target gradient play, they satisfy those conditions. Okay, non-universality. Okay, so we now have a structure that can stabilize any mixed strategy Nash equilibrium, isolated. We know the structure, but the coefficients are sensitive to the game, and the non-universality says, give me any one of those high order learning rules, I can construct a game for which it doesn't work. And we'll do that in 2 ways. One way will be to kind of cheap and easy, to just take the anti-coordination game and scale the utility function. And this could be considered as a problem for a learning rule. If a learning rule works, it should continue to work if you change the currency. But all we're going to do is we're going to scale the utility function of one of the players. And it turns out that if higher order target gradient play works for the anti-coordination game, scale the utility function of one of the players up or down, it'll stop working. Working here means being stable, okay? The analysis is actually a tool that's used in undergraduate controls classes. We like to analyze feedback loops that have an isolated parameter and ask what happens when this parameter gets large and what happens when this parameter gets small. And we can go through the analysis and say that when this parameter is large, which is the scaling of the utility function, or when it's small, this system will go unstable. And in my community, we like to just feel good. This is instant gratification to say, hey, look, the plot matches what we said is going to happen. So this is,
And the reason you can't build descaling into the rule is that it's a fact about the game that you would have to...
No, I mean, another rule, I'll have another way to prove the same statement where you can't build scaling into the rule. Because it just follows the letter P, you can scale the letter P. Okay, yes, please.
Is that mu or
No, for large, so what's happening here is for large mu, it goes unstable. This is the right half complex plane. And for small mu, also, it's unstable. Yeah, so up or down, yeah. But there is this middle ground where it's not too hot and not too cold, yeah. We can prove this a different way that's a bit smarter and extends to other learning rules. Here we have 2 structures. There's player 1, 2, 3, and 4. Players 1 and 2 want to match. Players 3 and 4 want to mismatch. So in the picture on the right, they're playing matching pennies with each other, 1 and 4, 2 and 3. But you take, remember, for us, a player is a learning rule. You take those learning rules with these utility functions and put them on the one on the left. And this also has a mixed strategy Nash equilibrium, non-unique. Okay, this one also has pure equilibria. And if it's stable on the right, it's unstable on the left. If it's stable on the left, it's unstable on the right. And that has nothing to do with scaling of utility function. It can't work in both places. Okay. Okay, so now the part that I think is actually perhaps most interesting is the connection to irrationality. We can learn any isolated mixed strategy Nash equilibrium, that's different from saying, should we learn any mixed strategy isolated Nash equilibrium? And here you see the phase diagram of, I don't even remember which one this is, but it's your favorite learning rule, standard order for a coordination game. So they're going to maybe approach this coordination game has two pure equilibria and one mixed equilibria. It zooms in and then zooms out to one of the pure equilibria. And so we know that we can construct higher order target gradient play that will converge to this equilibrium. But is that reasonable? Is that an unnatural learning rule? We'd like to add to the discussion of what constitutes unnatural. It is uncoupled. We're going to argue that it's unnatural as well. And so you can start, and I think this is also related to Christos's talk, if we're not going to be committed to replicator dynamics, then what are the requirements? Okay, if I don't want to commit to one dynamical rule, but let's put on some requirements on the different dynamical rules, say this one is eligible to be for consideration. So we agree that uncoupled is required. What else? And what we'd like to add to it is something called asymptotic best response. Okay? So an asymptotic best response, remember we're thinking of our systems as an open system. I'm responding to this letter P. If the letter P converges to a constant, asymptotically, X, the strategy, will converge to a best response to that constant. That's it. That's asymptotic best response. So yes, please.
Sorry, just a question because I want to make sure I'm not understanding the wrong thing. Is it the same or related as to saying that if other players converge somewhere in their trajectory, then I'm converging to the best response
Yes.
of whatever
It implies that, yes.
Okay.
It implies that. Yeah. Yes, yes. Because remember where the letter P is coming from. It's coming from the feedback loop, which is the other players. Okay? Okay, thank you for that. So we're going to call this asymptotic best response. If it converges to 1098, then asymptotically the output is 100. If it converges to 8910, then asymptotically the output is 001. And I think this is put this with uncoupledness as a reasonable requirement. Yes, please.
If I converge to 10, 10, 10,
And then anything goes. Anything goes.
best response set.
Yeah, anything go. Everything is a best response set.
But not to a point in the set. Right?
No,
Best
no,
response
no, not
set.
necessarily. Yeah, yeah. Yeah, so it converges, yeah, to what, yeah, best response set, but not necessarily converge, yeah, to a point. Correct, correct. And so this is not the phase diagram of a higher order because higher order has states that are not illustrated here. This is just to bring, jog one's memory. But we can say the following. If target gradient play higher order converges to this mixed equilibrium, then it fails asymptotic best response. Okay? And so it's an if and only if. So we can then try to argue that this equilibrium, which happens to have negative index, is not a reasonable equilibrium. And then we can argue that now from another angle of a dynamical or learning angle, that to learn this equilibrium requires a learning rule that fails asymptotic best response. So the results or the analysis is, again, from the controls literature. There's something called Strong's.
Any
Yes, please.
unstable equilibrium, that should be true, right?
No, no. No, we don't have something called unstable equilibrium.
Any minus one.
Minus one. Minus one.
That's a conjecture. Now, I just learned about sustainable equilibria 2 days ago. Okay, so that is a conjecture because if you go to the 3x3 coordination game, the mixed equilibrium has +1 index, and in fact, it is stabilizable with asymptotic best response.
That's the other way around. That's the other direction.
Yeah. So then, so it's, yes.
If it's -1, then
If it's
the
-1,
same
so-
thing that you build here must happen there. There is
Yeah.
a direction in which you can run away,
Yeah.
but since you are forcing this reply, it can't, this is
Yeah, so
the
it's a
other way.
conjecture now to connect strong stabilizability to negative
But
index.
the fact that you can make the equilibrium unique by adding strategies, you can
Everything we do is fully mixed. And so we haven't analyzed
fully
what
mixed.
happened. Fully mixed. Yes, I should have said that. Yes. This ends up being the sparsity structure of the system that is being stabilized. And there were results in the 70s that said a linear system is strongly stabilizable if and only if it satisfies something called the parity interlacing principle. I won't say what that is. It boils down to these two things having the same sign, and which they do in the 2x2 coordination game. But if you analyze this in the 3x3 coordination game, it does satisfy the parity interlacing principle. It is stabilizable by a stable dynamical system. Now, what's the connection to stabilizable by a stable dynamical system? This is I didn't mention that before. So I didn't lie to you, but I gave you a partial truth. Okay, remember we have this washout filter, and the washout filter is such that if P converges, then Y shuts off. If Y shuts off, that doesn't mean that U shuts off. Okay, if this is a stable system, if Y shuts off, then U shuts off. But if this is an unstable system, Y can kick it, shut off, and what's coming out of the higher order term continues to be active. So we need this second, the post-processing to be stable, to have the property that if P converges to a constant, then the whole upper channel shuts off. But there are some equilibria, like the mixed equilibrium of a coordination game, for which that is not possible. If we're going to get stability for that equilibrium, this upper system has to be unstable, necessarily. Okay, so the E is going to be, have a positive eigenvalue. But if the E has all negative eigenvalues, then we're in business. Okay, so the higher order, for some equilibria, the higher order modification must be unstable, which will then interfere with asymptotic best response. So I only have a couple more slides just to recap. To toot the horn of my community, I'm not going to say the game theory stuff. I'm going to say decentralized stabilization, simultaneous stabilization, a strong stabilization. That's what worked. Okay, what's what kind of provided the tools. And the enabler is to think of learning as an open system and then use feedback system perspectives. Extensions, we can do similar things for regular equilibria and beyond polymatrix games. Instead of target gradient play, let replicator dynamics be your baseline dynamics. Then have higher order replicator dynamics, whatever. We can do similar things. And everything I said also can be modified to the bandit setting, where it's discrete time stochastic and you're only measuring your payoff day by day, not just the differential equations. So I'll close out with some of the more recent work. That now that we're thinking about, hopefully, learning dynamics as an open system, we really don't want to go inside the box. We'd like to know what properties does this open system have without looking inside the box. What are the input-output properties? That's what we're going to do at the high level, and then at the low level, we're going to see, oh, this learning rule actually does satisfy that property. But we can say a lot about a learning in games without ever looking inside the box. This is something that the community does already. If you look at No Regret, and this is a very nice paper of Pilioris that recognized this. This is an input-output property that the inner product of the letter P and the evolution is going to grow at a sublinear rate. That's an input-output property. Another input-output property that is very much related to stable games and contractive games is that the flow of the strategy and the flow of the stimulus in the long run are correlated. Okay? That is called different names, delta passivity, delta dissipativity. And if you take any learning rule that satisfies this and put it with a strictly contractive game, you're going to get stability. And then low level, you say, what has it? This input-output perspective, I'm starting it off with Hofbauer and Sandholm because that ended up being monotonicity/dissipativity. It's taken on a life of its own in the largely in the controls community. So I'll conclude with a quote. Peyton Young said, "This is the imperial age of game theory." This quote is a little bit dated, but maybe we can say this is the imperial age of multi-agent AI. Tomato, tomato, okay? It's similar issues there's similar issues at play. And Vincent brought this up. You look at some of these risks that are brought up in this paper. Destabilizing dynamics. I mean, how custom made is that? All right. So I think that is a very rich time actually for learning in games, not so much to connect it to solution concepts, but to help us get a sense of what's going to happen in the world with all of these learning agents released in the wild. Well, thank you. I think it goes beyond that, yeah. But it's a perspective that has been visited by different communities and is now being kind of regaining popularity even in optimization, where the algorithm is up here and the objective function and constraints are down there.
And what are the normal concepts in control theory about open loop and closed? Because I see them a lot, but is it like leader follower and or direct?
No, just as you've said, an open loop, closed loop, okay? Feedback, no feedback. Yeah. And then people ask different questions of, can I stabilize under this condition, under that condition? So we looked at diagonal, can I stabilize using a stable controller, in these kind of things, yeah.
Your PI is still, you look at the product of the PIs in some sense. They are still, each player has his own PI. How about having a joint PI, a joint P?
What to do with it?
Whatever you do with
it becomes centralized. I mean, it fails uncoupled.
No, because that's going to be affected by, I see. The PI is the way that the game, that my payoff function affects the dynamic, right?
My learning, yes. Yes. But I don't want, I'm not allowed to get other
I know.
things.
I know. I'm trying to phrase something, but I don't know exactly how. Okay.
Sergio's at a loss for words. Okay.
No, I wanted to add, okay. Okay. Momentarily. Okay. Let's add to the state space the joint actions. So rather than looking on the product of the simplices, which is the xi's, right? X1 up to, yeah? Let's look at Z, which lives in the space of, so as a state variable, which is something we observe. So we look somehow at the joint action, and because things may move together, what you do and what I do may move together, rather than thinking of those as independent variables. Now that should allow you to do much more things, and the question is what?
So I'll take one step in that direction. Our dynamics had this additive higher order. There are investigations where I look at my own xi and feed it back through dynamics. So I'm not looking at other xi's, but I take my own xi and feed it back, and you can modify some of the input-output properties of a learning rule to make it stabilize more games. You can expand the set of games for which it is stable by doing maneuvers like that, of looking at my own xi and feeding it back. Now, if I'm allowed to measure the other xi's, and that maintains uncoupledness, as you've said, I am not sure of what else can be done. That's an interesting question. It could make the transition to the bandit case harder, the presumption that I can look at the actions of others. This one, the transition to bandit case was pretty straightforward because this payoff vector is related to payoff observations, payoff observables, and I'm oblivious to how many other players there are. But I don't have a good answer of what if I'm allowed to look at all of the x's and add that to my dynamics.
Am I allowed another question?
Can I ask a question?
I'll ask you.
Jeff, I have a question. Perhaps two questions. Let's go to online optimization. So your tools, in principle, you can use them also in online optimization.
What do you want to do in online optimization?
Question. So that's my
Yeah.
question.
Uh,
So is there any?
I mean, our learning.
Do you hire,
our-
let's say, sorry, does higher order replicator dynamic has some regret properties? This I don't know. I know that it is not true, for example, but in your world of higher order dynamics, can you construct
We're exploring things like
good
that. Yes.
non-regret strategies?
Yeah, we're exploring things like
Okay.
that.